Hello everyone. Am I audible? Atria, can you confirm? Okay, I think we'll start with the linear session then. Yeah. So hi guys. I'm Manshu and I conducted the first part of the linear session, the second session of our summer school, and we talked about matrices and introduced a bit of linear algebra back then. So yeah, coming like going through linear algebra, we come to more intuitive and abstract like concepts now. But I'd like to recap inner product and norm because it will be useful for what we're gonna learn now. So inner product, as I mentioned last time, is nothing but the dot product of two vectors. So actually we denote it with this because this is like a general way of denoting it. And in inner product, and this is like the dot product as we know. And well, this is for like if the v1, v2, w1, w2 are real numbers, right? So if they were complex, then I would like to represent like this. It's just a representation. And then we have the norm of the vector, uh, which is nothing but the magnitude of the vector. So these are like the basic stuff that we need to keep in mind. And there are some properties of norm. If you want, you can take a screenshot of this and just note them down. Um, I mean, these are just like properties. You can easily prove them. It's up to you. Parallelogram law, and then you can just expand these norms and then get this Cauchy-Schwarz. This is actually a good one. Try proving this. Then triangle equality inequality, we know this from like middle school, and reverse triangle inequality again is just inverse this. So yeah, you can go through these. Orthonormal vectors. Okay, so we have heard of orthogonal vectors. We know what orthogonality means. It means when two things are perpendicular. So orthogonal vectors are the vectors which are perpendicular to each other. So what is orthonormal or what is orthonormality? In a simple words, orthonormality means two things are perpendicular and their magnitudes are one, right? So if I say what are orthonormal vectors, then a set of vectors are called orthonormal. If a vector is or if every vector in that vector set has a magnitude or norm of one and is pairwise orthogonal. So if I have like a vector set S, which has v1, v2, v3, and so on till vm or vn, then these take v1, its magnitude is going to be 1, and it'll be orthogonal or it will be perpendicular to v2, v3, and so on till vn. So this is nothing but orthonormal set or orthonormal vectors. We actually have a good way of denoting this. It is denoted by Krochner delta function, Krochner delta. In this, I mean, it's just a name. If you see over here, Vi, Vj, where I and j are in the range 1 and n, inclusive of 1 and n, of course. That just means that V1, like it could be V1, V2, V3, or anything like between V1 and Vn, right? If I take V1 and some, let's say, for example, V2 and V2. That is, if I take I is equal to 2 and j is equal to 2. So it's just dot product of the vector with itself. What is that? It gives us the magnitude or the norm of the vector, right? And we know the magnitude is 1 in an orthonormal set. So here we get 1 if I is equal to j. And if I is not equal to j, let's say I is equal to 2 and j is equal to 3. In that case, it's like multiplying, it's like the dot product of v2 and v3. And we know in an orthonormal set, every vector is perpendicular to uh, like the vector apart from itself in the set. So v2 will be perpendicular to v1, v3, v4, so on till vn. So v2 dot v3 will be 0. And yeah, this is nothing but the Krochner delta. It's just like something that you can remember if you want to. But yeah, this thing. But yeah, the orthonormality, you get what the point is, right? So if there are any doubts, you can just ask in the meet. Orthonormal basis. Oh, actually, like if you guys have any doubts, you can like send it in chat, and Atreya or Girish, just please notify me so that I can clarify it. Yeah, orthonormal basis. Okay, I talked about basis last time. Basis. I'm not sure if everyone got what I tried to say, but again, what what it means, like to like what basis really means is that if you have a vector set, it can be of any vectors. And what I would like to do is I would like to find some fundamental vectors, some vectors which are like unique, right? And there will be some other vectors which could be like linear combination of these fundamental vectors. So what I want to do is I want to ignore those vectors. I mean, they can be in the vector space. I'm not taking them out of the vector space or the vector set. What I'm doing is I'm ignoring them and forming a new vector set, which is called as the basis, right? So this is what basis means. Now, if I have an orthonormal set, I want to form a basis of this orthonormal set. That is called the orthonormal basis of vector set. And yeah, there is like a really good way to form this vector set, and it's like quite easy to understand. It's called Gram-Schmidt's orthogonalization. It's a standard method, and we will look at what it really does, what we need to do to form a vector like orthonormal basis. Any doubts in orthonormal basis? You can just put it in the chat. Okay, Gram-Schmidt's orthogonalization. Let's say you have a vector set u1, u2, u3 till un, and I want to form a vector set v1, v2, v3, and so on, such that these like this vector set v1, v2, v3 is an orthonormal basis of our original vector set, which contains u1, u2, u3, and so on. Right. What do I do now? Okay, so first what I will try to do is I consider a reference vector. I will take a vector. It could be any of these actually, but let's say I'm taking u1, and that's a reference vector. I need to take this reference vector